For the first time, the conductivity of solid electrolytes was investigated in detail by Tubant, using a method similar to the heat-off method for electrolyte solutions. As an example, we can consider the experiments with the alpha modification of silver iodide. Tubant pressed 3 cylindrical tablets from silver iodide, weighed them, and clamped them between a silver anode and a platinum cathode with a known mass. To the electrical circuit was connected a coulometer to determine the amount of electricity. After passing the current, the tablets were separated and the tablets and electrodes were weighed. In experiments with alpha argentum iodide, it was found that the mass of the silver anode decreases, while the mass of the cathode increases by the same amount. The weight of the tablets does not change. So, the alpha argentum iodide has a purely cationic conductivity. The transfer number of the cation is equal to 1 and the transfer number of the anion is 0. Silver cations leave the anode in alpha argentum iodide, migrate to the cathode and then deposited on it. A similar experiment with solid plumbum chloride showed that the electrolyte has a purely anionic conductivity. Similar measurements have been made with a larger number of substances. Sometimes complications arise due to the fact that the metal not only deposited on the cathode, but also penetrated the tablets in the form of thin dendrites, eventually short-circuiting the electrodes. To prevent this phenomenon, tablets from other protective materials through which dendrites did not penetrate were sequentially included with the investigated materials. There were discovered some salts that have purely electronic conductivity. When the current passed through such substances, no changes in the masses of the tablets and electrodes occurred. Ionic conductivity and transport numbers strongly depend on the purity of the substances, as well as on the conditions for its preparation. These dependencies are the more significant the lower the temperature. The low temperature section of the conductivity curve is called the region of the improper or structure-sensitive conductivity. At higher temperatures, the conductivity ceases to depend on these factors. This temperature range is called the intrinsic conductivity region. The temperature range, in which the transition from structurally sensitive to intrinsic conductivity is carried out, depends on the degree of purity of the electrolyte. The intrinsic ionic conductivity of solids indicates the presence of defects in their crystal structure. Indeed, if the crystal were strictly ideal, then the transport of ions through it would be possible only through the exchange of places between the cation and the anion of the lattice. However, calculations show that this exchange is extremely unlikely, since it requires a large amount of energy.